going to be talking about a very important concept in organic chemistry, precisely the area that has to do with the alkynes. Now we're going to be looking at one of the important reaction of the alkynes, which is the substitution reaction of the alkynes. Before we go into the substitution reaction of the alkynes in proper, which has to do with the silver and the copper ammonia solutions, all right, to react with alkynes to form the acetylide. Before we go there, we need to understand the basis of the substitution reaction for the alkynes. All right, we need to understand the basis. Now, in order to understand the basis, I took my time to bring out this for you. Now, this is the foundation you are going to build on, all right, as we proceed. Now, like what is stated here, the acidic property. So the substitution reaction of the alkynes is an acidic property of the alkyne. How come is it an acidic property? Now, this is what this right up here is trying to put to us, all right? The reason why it is the acidic property, why we call it acidic property. Now, let's go into this. It says, when triply bonded carbon atoms are attached to a hydrogen atom, the triple bond pulls off the electron pair of the carbon and hydrogen. So if you take, for example, we have this, let's use ethyne. So we got this. Now, what happens is that this triple bond tends to what? Pull electrons. All right? The triple bond tends to pull electrons. You can see it. So pulls up electron pair of the CH bond. All right? So this guy, this triple bond is pulling electrons from here and from here. So due to that pull of electron pair from these two directions, it will now result in the weakening, all right, in the weakening of what? This hydrogen, this bond holding this hydrogen, and this bond holding this hydrogen. So because the triple bond is pulling electrons to itself from these two sides, it causes what? The bonding around here to become weak, all right. Now, if the bonding, all right, the bond here and here becomes weak, what happens? It therefore means that these two hydrogens are prone to removal, or in other words, it therefore means that these two hydrogens are prone to replacement. Are you with me? It means these two hydrogens are prone to what? Replacement. So because this triple bond is pulling the electrons from this side and this side, it therefore means that the bond between this carbon and this H and this carbon and this H becomes very weak. So this H can easily be removed, and this other H here can easily be removed. Now, what is used to remove them? It is what? A base. All right? So, weakening the bond, the hydrogen is readily removed by a base, making the alkyne acidic. So, what is used to eventually remove this hydrogen is with the help of a base. Are you with me? So, with the help of a base, this is removed and this is removed. Now, for this concept, for this aspect we are dealing with, the acidic property or the substitution reaction of the alkynes, the base that is generally accepted to be used in this reaction is a base called sodium amide. Please don't forget this. Don't forget this. Sodium amide is the base that is what? Used for this reaction. And it's written like this, NaNH2. Sodium amide. This is the base. All right? This is the base that is used to remove the hydrogen from ethyne. This hydrogen here and this hydrogen here. Why? Why is it possible for these two hydrogen to be removed? Because this triple bond has pulled, all right, it has pulled electron pairs from this side to itself. So these bonds are now what? Very weak. Now, this is what now makes this ethyne to behave as an acid. So that's why I call it acidic property. Okay? So that behaves like an acid. Now remember, an acid, okay, they lose what? Proton, hydrogen, they lose proton H. Okay? it loses proton. So because this ethyne can lose this proton, it therefore now behave as an acid. So it's now having this acidic property, alright, whereby it is able to lose what? The hydrogen. It is able to lose what now? The proton. Are you getting it? Alright, so since this is very clear, and then our base is also very clear, I will want to also state, please take note of this, I will also want to state, right, I will also want to state that only terminal alkynes, what are terminal alkynes? Alkynes with triple bonds between first and second carbon. So please take note, only terminal alkynes can undergo the substitution reaction of the alkynes. So only a terminal alkyne can undergo what? This substitution reaction of alkyne, or only a terminal alkyne can have this acidic property. Alright, so only terminal alkynes have this acidic property, or you can also say only terminal alkynes can undergo substitution reaction of alkynes. Now terminal alkynes have the triple bond between the first and second carbon. So the triple bond is either at the first and second from the right hand side, or the first and second carbon atoms from the left, whatever it is. So take for example, now I give you something like this, CH3, CH2, C triple bond, CH. Now you observe that the triple bond is between carbon 1 and 2 from on our right hand side. Alright, on our right hand side is between carbon 1 and 2. Then sometimes we can also rearrange this. Alright, this is a terminal alkyne. You can also do this. CH, yeah, and I put triple bond, then C, then CH2, CH3. This is also a terminal alkyne because the triple bond is between what? The first and the second carbon at the left. So whether the triple bond is between the first and second carbon atoms from the left, or between the first and second carbon atoms from the right, all that matters is that the triple bond is present between the first and second carbon atoms. So this type of alkynes, they are called terminal alkynes, and they are the only alkynes that undergo the substitution reaction, which is a peculiar reaction to the alkynes. Alright, so let's move. Now, practically, let me show you how this works. The remover, please take note. Take note again. The remover of acidic hydrogen. So you know why we now call this acidic hydrogen? You know why we are calling it acidic hydrogen? Because the hydrogen behaves like an acid, can be what now? Removed. Alright, so we call it acidic hydrogen. Okay, so the remover of the acidic hydrogen, alright, in a terminal alkyne, forms an acetylide. So when this hydrogen is removed, now remember, it's not just going to be empty, right? Something will take the place of the hydrogen. We are going to go into that in just a moment. Something is going to take the place of this hydrogen, or this hydrogen, any of the direction we want to use. All right, so that replacement, the removal of this, the hydrogen, and the replacement with something else, is usually a group, or most times it's always a metal. So it can be a metal or another group, right? Probably an alkyl group. Okay, so that the removal of the hydrogen, then the addition of that group, what you will now call this, it will now be what? An acetylide. Alright, so when you get the word acetylide, what should come to your mind is an alkyne a terminal alkyne. When you hear the word acetylide, what will come to your mind is a terminal alkyne that the acidic hydrogen, how do you even know the acidic hydrogen? The hydrogen that is on the carbons carrying the triple bond. For example, these two carbons are the ones carrying the triple bond. So this hydrogen attached to this carbon is called the acidic hydrogen. These two carbons are the one carrying the triple bond. So the hydrogen attached to this guy is what now? The acidic hydrogen. These two carbons are the ones carrying the hydrogen. Sorry, these two carbons are the one carrying the triple bond. So the hydrogen attached to this carbon and this carbon, two of them, they are known as what? Acidic hydrogen. Are you getting it? So an acetylide, when you hear the word acetylide, I repeat myself, when you hear the word acetylide, acetylide simply means a terminal alkyne in which the acidic hydrogen has been replaced with a metal or a group, probably an alkyl group. Alright, so now let me explain all this. I mean, remember the base we are going to use is what? Sodium amide. So now look at this reaction. So we have HC triple bond, C then H. Alright, now this in the presence of our base, don't forget our base is what? Sodium amide. So now what will happen is that this sodium will kick off this hydrogen. Alright, this sodium will kick off this hydrogen, okay, and then become attached to this carbon. So you will now have something like this. Alright, so when it becomes attached to this carbon, you will have this HC triple bond, then C N A. Alright, then that hydrogen that leaves combined with our NH2 that is remaining. When you remove sodium from this compound, what will you have? NH2. So this hydrogen are left combined with this NH2 to give us what? Ammonia, NH3. Alright, NH3. So this guy, an acetylide, right, without the sodium, an acetylide in which when you take away the metal, for example, now if I just want to draw a normal acetylide, that's for ethyne now, okay, I just want to do the acetylide of ethyne. I don't want to put this sodium. You're going to have this HC. So this is what you are going to have. All right. Now this guy is a nucleophile. All right. It is a nucleophile. So it's going to combine with our sodium. So you can have this. You might see some books, they put it like this. They'll put a minus here, minus and then like this. Or better still, you can just take away this is what you're going to have. So same thing can also happen for this other side. Alright, same thing can also happen for this direction. Now one good thing about this this acetylide is that you can use the acetylide to create or you can use the acetylide to form a higher member of the alkynes. Right? Can use this acetylide to form a higher member of the alkyne. Now, for example, now we want to form, let's say we want to get let's talk about butane. Okay, we want to get butane. We want to create butane. What is it? We want to create what? Butane. Alright, but our acetylide, we want to create butane, but our acetylide is what? This, alright, HC triple bond CNA, right? Now all we simply need to do is to react this. Listen up. All we simply need to do is to react this our acetylide with an appropriate alkyl halide. We're going to react our acetylide with an appropriate alkyl halide. Okay, so what do I mean by appropriate alkyl halide? Since you want to form butane, so an alkyl halide, I've dropped videos about alkyl. Alright, please do it to go and check that video. Now, an alkyl halide means alkyl group attached to an halogen, any halogen. And you know, in organic chemistry, literally, anytime you see the word X always stands for what? An halogen. Then anytime you see the word arrow always represents what? An alkyl group. Alright? So we want to get butane. We already have 2 carbons here. So how many carbons do we need to get butane? We need extra 2. So therefore means that our alkyl halide is going to be ethyl halide. Ethyl halide, because ethyl has 2 carbons. And to get our ethyl halide, you can write it as C2H5X. That's our halide. So we can say, okay, let X be chlorine. Or okay, we can say bromine. We say S is bromine, BRO. For example, S is bromine. Or we can use chlorine, and any one you decide to use. So if we say it is bromine, PRO. Now, what will be our product? What will be our product? So we are going to get HC123, then see this sodium, we get attached to bromine. So we have NaBRO. That's very settled, right? Then this our alkyl will come here. We have this, then we now have C2H5. So this is it. So we have gotten butane, all right, aka but1-ine. I can still decide to rewrite this as CH2CH3. Okay, CH2CH3. So you can see that this is similar to this. Are you seeing it? This, what we got here, look at it. So that's the benefit of the acetylide. You can use the acetylide to generate higher members of what now? Of the alkynes. Okay, so that is it. Now we can also remove this other hydrogen if you decide to take it out. So in order to remove this hydrogen, what you simply do is that you want to also remove this hydrogen. You simply use your sodium amide. So it will be this again reacting with what? Sodium amide. Or you can just use this guy, for example. No need to use this anymore. Just use this. Or you can form another acetylide that you want to use. Or if not an acetylide, you can just think about any other terminal alkynes you can also use. So from this guy, we have removed this hydrogen here, replace it with sodium, and later replace it with what? An alkyl group. So this thing we are doing is substitution. What does substitution means? You are removing one thing, you are replacing with another. When you watch a football match, you will see one player at the bench, another is in the field. So when it's time to substitute, that one playing in the field will be removed. The one on the bench will come to take his position. All right. So that is the same thing that is happening in this reaction. So, but then if we also want to remove this H, this acidic hydrogen, want to also substitute. Remember, only the acidic hydrogen in a terminal alkyne can be substituted. So if you want to substitute this hydrogen, basically it's the same thing. All right. You react this with our sodium amide. Sodium will come here, and then this hydrogen combine with this NH2 to give us our ammonia. All right. Then you can still use that same one to generate a higher member of the alkyne again. That will also be your choice. But this is the basic concept. All right. This is the basic concept you need to know. Now let us go into the actual or the most famous. Let me use that word. Let's go to the most famous substitution reaction of the alkyne. Now you understand the step and the principle. All right. Now let's go to one of the most famous substitution reaction of the alkynes. Reaction with ammoniacal silver 1 nitrate and reaction with ammoniacal copper 1 chloride. So these two are the most popular substitution reaction of the alkynes. All right. So now let's take ethane. Reacting with this guy. So that is our ammoniacal silver 1 nitrate. So what are we going to have? Remember this substitution. Let's just assume that I want to substitute the two hydrogen. So we are going to have are you there? And then we have okay. Remember, we use 2 silver, so we are going to put 2 here. Okay. So then This is a reaction. And so this is the balanced chemical equation for this reaction, all right, for the first one. So this is everything. Then for the second one, all right, reaction with ammoniacal copper 1 chloride. So how do we do this now? Still very, very easy. All right, so let's use ethyne again. So HC triple three, then why are we using ethyne? Because ethyne is a terminal alkyne, because it only has two carbon 1 and carbon 2, and the triple bond is found between what? Carbon 1 and carbon 2. So this first and second, from this other side, first and second, the same thing. So plus ammoniacal copper 1 chloride, what do we have? Cu NH3 Cl. So this reaction, let's replace both acidic hydrogen. So we're going to have, right, replace both acidic hydrogen. Then the two hydrogen, right, so we're going to have, our product is going to be this and this guy. So that will be our product, right? All right, so for these two, okay, one thing you need to know is that both are unstable, all right? So they are readily decomposed by mineral acid, okay? So this and this, all right, silver 1 acetylide and copper 1 acetylide, both of them, they are unstable and they are readily decomposed by mineral acid, okay? They are decomposed by mineral acid. Now, when we're talking about mineral acid, what do we mean? We're talking about inorganic acid like hydrochloric acid, HCl. So this is what we're going to have. If we just pick this guy as an example, or any of them, so we'll go like this as Ag. Then we have this. We actually mineral acid like HCl. Okay. So what we are going to get, remember they are very unstable, they are easily decomposed. So they are going to decompose to give us our alkyne, all right? Remember we used ethyne, we converted ethyne to this. So because this guy is unstable, and when they react with mineral acid like hydrochloric acid, mineral acid simply means inorganic acid. So hydrochloric acid, HCl, all right, is going to give us back our what? Alkyne, which is ethyne. So we're going to have HCH plus AgCl, right? So by the time we balance, we'll put 2 here, and then we'll put 2 here. The final thing we're going to talk about is the hydrolysis of acetylide, all right? Acetylide, hydrolysis of acetylide. Hydrolysis of acetylide. Now, when we are talking about hydrolysis, what does hydrolysis mean? Hydrolysis means using water to cause breakdown to a compound. So when you use water to cause breakdown to a compound, you have carried out what? Hydrolysis. So hydrolysis of acetylide. All right, now acetylide, like we can use maybe the first guy that we did before. We can use this guy. Remember, I told you acetylide. What is the meaning of acetylide? Please, let's not forget. I repeat, let's not forget. Acetylide is when the acidic hydrogen in terminal alkynes has been replaced either by a group or by a metal. It could be an alkyl group. It could be what? A metal. Right? So long the acidic hydrogen in terminal alkyne is being replaced by metal or any other group, it forms what? An acetylide. So when we carry out this hydrolysis, all right, so it's going to give us back. It's going to give us back our sign. So we're going to have this H like this. So this is what we have. All right. So thank you very much for watching this video lesson. Please do well to like this video, all right, and subscribe. Now see you in the next video lesson.